We are gonna go over the exam. We're gonna finish ideal gases, and then we may even start phonons. So really a lot to do. So let me do the announcements, and then we'll talk about the exam. So first announcement is I haven't posted your grades, but I'll post them later today. So midterm grades posted today. What I've been doing is I've been marking on your exam grades for every problem, so you see what you got on every problem, and maybe little comments here and there if I thought they were important. You know, I have to do it in Adobe, so it's kind of annoying, but I think it will work. Let's see, you have a homework due Thursday. There's problems at 5. Okay. And 3, read Macquarie chapter 6, because that's the chapter on ideal diatomics, and we're going to finish that today. Okay, so read Macquarie chapter 6. Okay, so those are the announcements. So let's do the exam. So, I don't want to spend a ton of time talking about the exam. Hopefully after you took the exam, you thought more about the problems and you've already figured out what you did right and wrong. Right? So I hope that's the case. So here's the grading. An A is if you got it between 75 and 100. I think that's a pretty fair scale. B is if you got between 50 and 75, and C is if you got less than 50. Okay. The highest grade was, I think, around a 95. So I think the exam was doable, and that's a fair scale. All A's and B's. I don't think anyone got a C. So everyone got an A or B. If you got a higher B and you've been doing pretty well in the homework, then you probably have an A in the class. If you got a lower B, you probably have a B in the class. So to get an A, do better on the final exam and the Monte Carlo. Okay? And you'll see your grades later today. Does that sound fair? Everyone happy with that? Okay. Let's go over it. And I'm gonna sort of pick and choose what to go over based on what people got right and wrong. So the first problem, I wanted you to derive, and if you want to take notes, maybe take notes because I'm not gonna post these solutions. Sorry. Usually I post solutions, but I'm not going to post these for exam. I want you to derive this. N equals dPV d mu, a constant V and T, from A from thermo, which I'm not going to go over. Most of you got right. There you use a Gibbs-Duhem. Okay. And then I wanted you to derive them from StatMag. Okay. Many of you used an equation from table 3.1, which actually was not what I was looking for. So some used this equation. And this was an equation that that was in your book. And so that would be an okay, that's essentially your answer for A, because all you're doing is substituting KT log partition function is PV. So 2 reasons, I gave you partial credit for that, but it wasn't what I was looking for. The reason was, this comes from thermodynamics, really, right? And it's not a derivation, right? And I wanted you to derive it. So from StatMag, to derive these things, what you want to do is take the derivative of the partition function, right? So just like when we were deriving E equals d beta a d beta, I want you to crank through this derivative using the probability of StatMag, right? So that's how you derive it. So for B, what I wanted you to do is use the relation PV equals KVT log partition function, and then take this derivative. And so if you take this derivative, d PV d mu, the derivative of the log gives you 1 over c, right? So you get KBT over, that's the derivative of the log, but then you have to take the derivative of the partition function, right? So then you need d mu of the sum over n. This is grand canonical partition function, so you need a sum over particles and states, right? E to the beta mu n, e to the beta e I. Okay. Be really careful. Some of you, I see this mistake every year. Some of you like to take logs inside sums. Can't do that, right? There's no way you can take this log inside the sum. Think of a sum like an integral. You can't take a log inside a sum. You can take a derivative inside a sum, right? Just like you can take a derivative inside an integral. So this derivative can go inside the sum because the sum is over n and I, mu is independent of those. So you bring the derivative inside the sum, this pulls down the beta n, right? The beta cancels the KBT, you get 1 over, well, let me just write it out. You get KBT over C. Derivative goes inside the sum, you get sum over n, I. You pull down a beta and an n, so you have beta n, e to the beta mu, n, e to the beta e, I. Okay, and of course the beta cancels for the KBT. This C you can bring inside the sum because it's just a constant. And so this equals sum over n, I, n, right here. And all this other stuff is your probability, right? The exponentials over C is a probability of n and I. So n, p, n, I. And that's the definition of an average. And so that's average n. Right, so that's what I wanted you to do. And so basically, stat mech, you always equate an ensemble average with a thermodynamic quantity. And basically the derivatives, when you take a derivative of the log of a partition function, in general, it will give you an ensemble average, if you can do it right. Does that make sense? Okay, so that's how I wanted you to do 1B. 1A I think was fine. How about 2? So 2 was actually a homework problem, an unofficial homework problem. So the nice thing about having my lectures videotaped is I have records of everything. So if you remember, there was one time in lecture when we were going over the ideal gas, and I gave you an unofficial homework problem, which was to think how you could apply that to homework problem 4.2. So if you want to see this, this was a unofficial homework problem. You know, all the lectures are online, so if you look at lecture, this was lecture 10.1. If you go to the 32nd minute of lecture 10.1, you'll see that I assigned this problem as an unofficial homework problem. Okay, and the point was it's the same as your homework problem 4.2, but I wanted you to solve it differently, right? And I wanted you to solve it with the same way we solve ideal particles. And so what this was is you have n non-interacting particles. Each can have energy 0 or epsilon. Whoa, that's not epsilon. Okay. And you know, draw out pictures if you want. The best way to think about this is you have a 2-state system for each particle, right? So each particle can be in one of 2 states, and you have n of them. So this is your system. You have n 2-state particles, right? And this is energy 0, this is energy epsilon, and you have n of these. And they're all independent, so they can all do whatever they want, right? So this one could be in the ground state, this one could be excited state, this could be excited state, this could be ground state, this could be ground state, dot, dot, dot. Right? And so when you draw this picture, hopefully what you realize is that the state of the system is basically the state of all these different particles, and all possible states of the system are all possible arrangements of the particles between the ground and excited level, right? And so when you solve for Q, Q is the partition function of the system, you always write down the naive formula, right? This is always your naive formula. And it's your job as stat mech practitioners to figure out what the naive formula means for your particular problem, right? Because I is just an arbitrary state index, right? So what your job was is to figure out what this I is. And what I is a particular arrangement of all the particles in these different states. Okay? So to sum over I, what I really need to do is I need to sum over all the particles being in 0 or excited. 0, excited, 0, excited. So what you can do, and they're all independent, right? So if this is particle 0, and this is particle 1, this is particle 2, this is particle 3, this is particle 4, what I can do is I can sum over the energy of particle 1, call it, say that the energy of particle I, epsilon I, can be 0 or epsilon. Okay? And so I can sum over the energy of particle 1, epsilon I can be 0 or epsilon. Right? The second particle is independent of particle 1, so then I have to sum over epsilon 2 can be 0 or epsilon. The third particle is independent of particle 1 and 2, so then I have to sum over epsilon 3 equals 0 or epsilon, right? And this is analogous to what we did for the ideal gas. So we have n of these sums for the n different particles, summing over the two different states. We have e to the minus beta. Oh yeah, and the other thing I need to write down is my total energy, E, is just the sum of the energies of the different particles, right? So it's just E1 plus E2 plus E3 plus E4. Just like the ideal gas. And so I plug that in here for my E, E1 plus E2 plus E3 plus E4 plus dot dot dot. And it looks the same as my ideal gas because they're non-interacting. And so then the trick is to realize that each of these sums is independent. The exponent factors, and so you can write this as the sum over E1 is independent with a e to the minus beta E1 term from the exponent. That multiplies the sum over E2, which is independent, with a e to the minus beta E2 in the exponent, dot, dot, dot. Okay? And so then you do these sums independently. Obviously, this thing in parentheses, when I have 0, I just get 1. When I have epsilon, I get plus e to the minus beta epsilon. All these are the same, so this thing is to the n. Right, so that's your final answer. Okay? And of course, this is your little q right here, right? This is little q. So it gives you the same form as the ideal gas. You have little q to the n, where little q now is just this because it's a two-state system. So that's what I was looking for in that problem. And it was really just realizing that the problem from homework 4.2, you could solve exactly the same way as the ideal gas. Questions? Questions on that one? Okay, what's next? 3, pretty much everyone did 3A right? 3 was, I gave you the potential energy surface for dihedrotation of butane, right? 3A was a canonical ensemble problem, okay? So I wanted you to tell me what is PI for gauche, trans configurations, etc. at 300K, right? So I'm specifying the temperature, so you're using your formula from the canonical ensemble. So this is canonical ensemble, right? And so you only have 3 states there, and so you just write, PI is either minus beta EI over Q, because you have 3 states. Q is a sum of just 3 terms, okay? 1 for gauche, 1 for trans, etc. So it's sum of 3 terms. So, I won't plug in the numbers, but I think everyone did that right. B, I tried to trick you a little bit. B, you need to use a microcanonical ensemble, right? So 3 was sort of to see if you could apply the canonical at constant temperature, if you could apply the microcanonical at constant energy, right? Because 3, what I say is now the energy is fixed, okay? Okay, now 7 butane molecules at fixed energy, what did I give? 15 kilojoules per mole, okay? Okay, and so the energy is fixed, so you have to apply the microcanonical ensemble. Okay. And that is that each state is equally probable. Okay? And so I asked you, what's the probability that any one of the 7 is in the eclipsed? And that's, so if they're in eclipsed, eclipsed has 15 kilojoules per mole. What did I say? The gauche has 3 and trans has 0, right? So gauche has 3 kilojoules per mole and trans is 0. Okay. So if the total energy is going to be 15, there's only 2 things I can do, right? I can have 1 in eclipsed. I could have 6 in trans. That gives me 15. Or I could have 5 in gauche and 2 in trans, right? Okay? And those are the only way to get 15. If these particles are indistinguishable, then this is one possibility, this is another, right? This is one state, this is another state. There's not multiple states here and not multiple states here because they're indistinguishable. So if they're indistinguishable, then the probability that one is in eclipsed is 1/2, right? Because I only have 2 states and one of them has eclipsed, right? So probability equals 1/2 for indistinguishable. Everyone see that? There's only 2 ways. They're both the same probability because I'm in the microcanonical ensemble. And there's only 2 ways because they're indistinguishable. If they're distinguishable then I have a combinatorics problem. Okay, so if they're distinguishable, then they're different states depending on which particle I put in eclipsed, right? Because they're distinguishable. So here, obviously, I could have 7 different situations, right? Any one of my 7 molecules could be in the eclipsed. So this has 7 states, right? So probability, I have 7 ways that one could be in the eclipsed. How many ways do I have that 5 can be in gauche, 2 can be in trans? That's 7 choose 5, right? So that's 21. So there's 21 of these possibilities. And so my normalization down here is 21 plus 7, right? Because I have 21 states here, I still have my 7 states here, and so I get 1/4. 7 over 28. Okay, so that's what I was looking for there. And so the main point of that problem was to realize the difference between when you apply the canonical probability distribution and when you apply the microcanonical, and then differences between distinguishable and indistinguishable particles. Okay, for most of you did right. 4 is just really hammering home this important concept in deriving the canonical ensemble, right? So I wanted you to prove this transformation. We've done this several times now, where we're calculating the average occupation of a given quantum state, and we said we could do it 2 different ways. We could sum over all the ways of making the ensemble alpha, write AI alpha over the total ways of generating the ensemble, and the key point was to prove that this sum is equivalent to a sum over occupation numbers, a vector, where we have the degeneracy, W of a vector, well, the number of ways of making the ensemble with that occupation vector, AI over T. So I wanted you to prove this for a toy system, right? And my toy system was that the number of copies is just 3. We have 3 different quantum states. So we have quantum state number 1, 2, 3. The energy of the quantum state is energy of 1 is 0, the energy of 2 is 1, and the energy of 3 is 2. And then we have the occupation number. This is just A1, A2, A3. So that's the model system, and I want basically if my total energy is 3, I want you to prove equivalence of sums for, you could calculate average A1, you could calculate average A2, average A3, you should get the same results. The sums are equivalent no matter what you put for the I. I just had you do it for average A2. I just picked one, okay? So what you do here is you think about all the different ways of making the ensemble that's consistent with this, right? And so your ways of making the ensemble is you have these 3 systems, right? And obviously you could choose this equal to E1 equals 0. This could be E2 equals 1. This could be E3 equals 2, right? That ends up to 3. Or you could they could all be 1, right? And so you could have 1, 1, 1 there. There's only one way of doing this. There's 6 ways of doing this, right? There's 6 ways. There's 6 ways. So really what I should say is your occupation vector could be it could be 1, 1, 1, right? 1, 1, 1 means that there's one system in quantum state 1, one system in quantum state 2, one system in quantum state 3. That's this. Or it could be 0, 3, 1. This is 0, 3, 1, where there's 0 systems in quantum state 1, there's 3 systems in quantum state 2, and 0 systems in quantum state 3, right? So it can be that or this, right? Those are the only possible occupation vectors, okay? And there's 6 ways of making the system with this occupation vector by just permuting all of these. And there's only one way of this, okay? And so what I want you, so if you did this sum on the left, so if you do the left sum, what you do is you sum over all the ways, and so you have 7 ways. You have 6 here and 1 there. So your sum over alpha, AI alpha over T equals, you're gonna have 7 terms in the sum. For these 6 ways, A2, sorry, this is a 2, right? Because I'm specifically doing average A2. For these ways, A2 is 1. So I have 6 1s, right? So equals 1 plus 1 plus 1 plus 1 plus 1. Plus 1. Okay? That's the sum of these 6 ways, putting in A2 alpha here. For this one, A2 is 3, and I only have 1 way there, so I have to add 3. And then my total is 7 ways, 6 plus 1. Okay? So that's the left sum. The right-hand side is, we don't sum over ways, we sum over occupation numbers, and then we have to put in the W, right? So we have W. Okay, so I only have 2 terms in the sum now, because I only have 2 sets of occupation numbers, but I have to multiply by the number of ways. So my first term in the sum is 6 ways for the W times 1 for A2, right? So I have 6 times 1. And then this is my second occupation vector, 0, 3, 1. I only have 1 way of making that, and A2 is 3 in here. Plus 1 times 3 over 7. And obviously you get the same thing. This is 9/7. This is 9/7. Right? And so that's what I was looking for. And you know, with this toy problem, it may look silly to belabor this point, but I think you appreciate that this is not such an easy concept. Right? I mean, when we were deriving the canonical ensemble, we spent a lot of time talking about this transformation. So it's worth going over simple examples to rationalize concepts that are not so easy or straightforward, right? So don't say, oh, this is a silly example, because it's important to illustrate this concept, this more complicated concept. Okay, so that's pretty much it. Everyone did number 5. I'm really happy about that, right? You also have a good idea of what P of E looks like. It looks like this delta function. Although, I don't think most of you, for B I said provide one justification or example for the scaling of sigma of E, right? So I want you to tell me what the scaling of right? And you know, what we say in class is it looks exponential. It looks like that. And that's the only way you get a delta function for the probability, because here's your Boltzmann factor, either minus beta E. And so your probability looks like this because they multiply, right? This is P of E. So, you know, we said it looks exponential, but what's a rigorous justification? Anyone know? Was anyone happy with their response on the exam? Thinking back to it, or did they just kind of throw something down? Just kind of threw something down. So I mean, the two things that I really wanted were either you talk about Macquarie's example, right? Macquarie actually computes this. Remember? I wish I had my book with me today. He computes this for non-interacting particles, essentially for an ideal gas. And he proves that this thing scales exponentially with E. Now, that's a 2-page proof, but it's a proof. So, you know, you could either have written down Macquarie's result for a gas of n particles and say, look, it's exponential. That's a proof for a model system. Or another proof is to think about entropy. That's what I would say, right? So you could use proof. You could use thermodynamics. You could use Boltzmann's entropy formula. You could say S is kBT log omega. Okay. You know that S has to be extensive, right? So this proves that omega of E must go as e to the n. It has to, right? It just has to, because if S is going to be extensive, this is not extensive, you better bring down an n when you take the log, right? So this has to be true for entropy to be extensive. Right? And then you know energy is extensive, so you know that E goes as n. Right? And so if you combine these two, then you know that this goes as exponentially with the energy. I mean, I really should put a proportionality here, but that's fine. You can bring it out front. So I would say that's the simplest argument, right? It's the simplest argument, but it's a really important argument because the fact that this thing is exponential, I mean, that's what gives you the real world. That's what gives you liquids and gases. If this thing weren't exponential, you wouldn't have 3 phases of matter. You would only have 1 phase of matter, right? If this thing's not exponential, you have a decay. Everything's a crystal. Right? So the fact that this is exponential has extreme consequences for physical chemistry. And so it's nice to have a simple rationalization in your head, which is just this. Okay? Okay, so I spent half hour talking about the exam, more than I had planned. But it's good to go through. Questions on that? Does that make sense? Yeah? Okay. I'd rather spend the time discussing it and you know, learning as we go forward. Okay. And like I said, I'm not gonna put solutions. So I hope you took notes on what you needed. Can I erase this part? So I'll post the grades today, and I will send you back your exams to each person with just a few marked up comments if necessary. And of course, send me questions if you have them. Okay, so let's see if we can finish gases, if we have time. That's our goal. Most likely we won't get a phone on, that's okay. 3 pages. 3 pages to finish gases. I think we can do it. So let's do that. Let's finish gases. So we are going to finish the thermodynamics of ideal Boltzmann diatomic gases. Okay, and where were we last time? hard to remember, but here's where we were last time. We split the partition function into a translational, a vibrational, and rotational part. So we said the total partition function Q was equal to a translational part times a vibrational part times a rotational part, T, V, and R. And then we define these things in terms of the single particle partition functions for translation, vibration, rotation, right? And so we said the QT has the 1 over n factorial term. It's the little q to the n, where this is the single molecule translational partition function. And then we have an n factorial on this one, okay? We don't have n factorials for the other one. So QV then is just little qv to the n, okay? And QR is little qr to the n. Okay, so that's, I think, where we ended last time. Everyone agree? Yeah? So let's do thermo. We know these guys, right? I'll write them down as we go, and so we can derive all of thermo. So, start with the free energy. So we use our expression Helmholtz free energy is minus kBT log big Q. When we take the log of a product, we get the sum of the logs. So the log splits these into 3 terms that add together, right? And so this becomes minus kBT log QT, the translational. You could call this a translational free energy. We call it AT, the translational free energy. And then we have minus kBT log QV, vibrational. You could call this free energy for AV, for vibration. And you could do minus kBT log QR. Okay? And so this is what, if you run an electronic structure code like Psi4 or Gaussian or games or something, this, and it spits out a free energy, this is what it's doing. Right? It's calculating a translational free energy, it's calculating a vibrational free energy, knowing something about vibrational frequencies, and a rotational, and it's adding them all up, and that's what it's spitting out if you do that kind of calculation. Okay, so that's fine. We could do this. We could plug those in. We're not going to do that right now. We're going to focus on the pressure and the energy. Those are the more interesting things. Well, the pressure's not too interesting, but we should do it at least. Okay, so let's do the pressure. We get the pressure by taking the derivative of the minus dA dV, right? The derivative of free energy with respect to volume, holding temperature and N fixed, okay? So what that means is I need to take the derivative of each of these 3 terms. Do these guys depend on volume? Vibration, rotation? Probably not, right? You can look back at your formulas, they don't. Intuitively, they shouldn't, right? A vibration and rotation doesn't depend on volume. Only this guy depends on volume, right? And so only the translational free energy depends on V. Right? And this part is exactly the same as for the monatomic ideal gas, right? And exactly same as for monatomic ideal gas. So I'm not going to go through the details, but for a monatomic gas, we prove PV equals nRT by taking this derivative, and you get the same thing, right? And so you get PV equals, in stat mech, we like to write big capital N KT instead of little n RT. Whatever you prefer. I like this version better. Thinking about number of atoms. Okay, so you get the ideal gas law. That's good. We're not going crazy, right? Sanity check. How about energy? Well, we're not going crazy in this classroom. Maybe in the rest of the world we're going crazy, but when we're in StatMech classroom, right, we have sanity. That's the beauty, right? Okay, so energy, we are going to use the formula we had before. If you look back in your notes, in the canonical ensemble, we have an expression E is kBt squared times, we have to take the derivative of log Q with respect to temperature. Okay? So that's our formula for the energy from the partition function. Again, I take the derivative of each term now, right? And so this gives me kBt squared times the derivative of the translational part. Let's call this the translational energy, ET, plus kBt squared times the vibrational part, okay, EV, okay, and then one more, the rotation, plus kBt squared times d log QR dt. ER. Okay, so we have energy for translation, energy for vibration, one for rotation, and they all sum together as you would expect. We've already done ET. It's the same as a monatomic gas, so we have to do these two. Those two are new. We haven't seen those before. Okay, and the key point of this lecture is equipartition. Okay, so the most interesting and important thing of lecture today is the equipartition theorem. And we're going to see it for all three terms. So keep that in your head. Equipartition, equipartition, equipartition. So let's write down the translational just to make our point. What we found for the monatomic gas was that ET is 3/2 NkBT, right? This is it's the same as the monatomic ideal gas, right? And the key point today, equipartition theorem says you have 1/2 kBt worth of energy in each degree of freedom, right? So that's our moral for the day. Equipartition, we talked about this before for the monatomic gas theorem, says you have 1/2 kBt average energy per degree of freedom. Did we have to qualify this? Is this true did we have to take a classical limit or something? Yes, we did. So this is true in the classical limit only, right? So this is in classical limit. Okay? And of course, that's what we have here because we have 3n degrees of translational, 3n degrees of freedom for translation, right? Okay, so let's do vibration and rotation and let's see the equipartition theorem for those. And hopefully that will convince you of its generality. So let's do vibration. We haven't done this. I need to take this derivative, okay? I'm going to write it a little differently. I can switch between a temperature derivative and a beta derivative with this kBt squared prefactor, right? So I'm just going to write it like this. I'm going to write, did I get my signs right? Yeah, no, I did. So I'm going to write EV, the vibrational energy, which is this term. I'm going to switch to a beta derivative, and I need a minus sign, and I get rid of this kBt squared. So it's minus dd beta log QB. Okay. So you guys have had practice converting between temperature and beta derivatives, right? And we always just get this factor when we switch them. Everyone okay with that? Yeah. Okay, so QV is little q to the n. Okay, so we're taking a log, so the n gets pulled out in front when we take the log, and so this is minus n d beta of log little qv. Okay, so then we have to look back in our notes and find our formula for little qv. Anyone remember how we solve for little qv? We used some mathematical trick. I think John figured it out. Yeah, we used a geometric series. That's right, Philip. So we used a geometric series to solve for little qv, and when we did little qv, we had this. Our 0-point energy contribution was on the numerator, e to the minus beta h bar omega over 2. That's your 0-point energy in the exponential. And our geometric series gave us 1 minus e to the minus beta h bar omega. Okay? That look familiar to everyone? That was from the geometric series. So we have to take the log of this whole thing and take its derivative. Okay? Let's do that. So we get E vibration is negative n d beta. Okay, we have to take the log of this. So we have a log of the numerator minus the log of the denominator. Log of the numerator just gives me minus beta h bar omega over 2. Okay, and then minus the log of the denominator. Minus log of 1 minus e to the minus beta h bar omega. Okay, everyone happy with that? So now let's take the derivative. Let's go over here. Take the derivative, so I get EV. I'm gonna pull a minus sign, this minus sign out. I'm gonna pull this minus sign out, and they're gonna cancel with this minus sign. So I'm gonna cancel my minus sign, and so I get EV equals just an n. Now I'm gonna take the derivative. Derivative first term is easy. I just get h bar omega over 2. Okay. Derivative of a log is 1 over what's inside times the derivative of what's inside. So I have plus something over 1 minus e to the minus beta h bar omega. Okay, and the numerator then is an exponent times minus h bar omega. But my minus sign cancels because I have a minus here and a minus sign here, right? So you get h bar omega e to the minus beta h bar omega. Everyone happy with that? Yeah? Okay, so that's my derivative. Now what am I going to do? I'm going to simplify it a little bit. I'm going to pull an h bar omega out of here. So I'm going to write EV equals n h bar omega. And then I'm gonna write this one second, just because it looks nicer that way. And so this term just gives me 1/2. So I'm gonna put my 1/2 right here. That's this term. This term, what I'm gonna do is I'm gonna multiply this term by e to the beta h bar omega over e to the beta h bar omega. I'm gonna multiply by 1. okay? If I multiply by e to the beta h bar omega over e to the beta h bar omega, the numerator becomes 1. This becomes e to the beta h bar omega, and this becomes 1. So let me just write it down, right? I get e to the, sorry, that one cancels out. I get 1 over e to the beta h bar omega, no minus sign, minus 1. Everyone see that? If I just multiply by e to the beta h bar omega over e to the beta h bar omega, yeah? Okay, then I'm almost done. I'm gonna define something. I'm gonna define a vibrational temperature. Just like I did for rotation, I'm going to define it as theta V, okay? It's got to have units of temperature, so it's got to have energy units over Boltzmann's constant. Energy units is this, h bar omega, and then over Boltzmann's constant. So that has units of energy. And I'm just going to plug that in to clean up my exponent a bit. And so my final expression that I'm going to circle is this, EV equals N h bar omega times 1 over e to theta V over T minus 1 plus 1/2. Okay, so that's my final expression. This is exact. Okay? This is an exact result for the average energy of a diatomic vibration at a given temperature, right? So this is exact. For harmonic vibration.
And the biggest one I made is the dihydrogen.
Okay. Exact means it's from quantum mechanics, right? A classical result isn't going to be exact. Let's think about the equipartition theorem, right? I just said here that equipartition theorem, I should have 1/2 kBT average energy per degree of freedom. Does this look like anything I could rearrange or write as 1/2 kBT average energy? Not really, right? It's not obvious. So it's not obvious how this satisfies equipartition, and the answer is it doesn't, generally, because we need to take the classical limit. Okay, so note that this, in general, is not equivalent to our expectation from equipartition okay. It only is if we take the classical limit. Okay? Only if we take classical limit. Okay, so that's an important point, is that if we have to treat something with quantum mechanics, in general we're not going to see equipartition, but only on the classical limit. So let's go over here and let's take the classical limit and prove that indeed it's true in the classical limit. Okay, so let's take the classical limit of EV. Okay? So, what do I need to do here? I need to look at how the energy of the harmonic oscillator compares to the temperature, right? So let me write that down and we'll discuss the classical limit. So this, it's important to know what magnitude theta v is for diatomics. So for typical diatomics, okay, theta v has units of temperature, and it's big. It's between about 500 and 5,000 Kelvin. Okay, so it's much bigger than room temperature, right? So note that at room temperature, T is less than theta v. Okay? So this limit I'm going to write down is only going to be true if we're at super, super, super high temperature. And this is because vibrations have to be treated with quantum mechanics, right? You know that. And so we have to be at a really, really, really high temperature to be able to treat vibrations with classical mechanics. And so what I'm going to do, so what follows is only true at very high temperatures, right? So the result isn't really that useful, except for the fact that we see equidistant. That's really the usefulness of this derivation. So let's assume, okay, so assume we're at such high temperatures that T is much, much greater than theta v. Okay? We're way hotter than 5,000 Kelvin. Maybe we're in the sun. I don't know. Okay? So if T is much, much greater than theta v, and I already defined theta v as being h bar omega over kb, right? This means that kBT is much, much greater than h bar omega. Everyone agree with that? Yeah? Remember when we talked about the classical limit, and we said the classical limit was when thermal energy, kBT, was much greater than the spacing between energy levels of quantum states? What is the spacing between energy levels in a harmonic oscillator? This, right? So note for a harmonic oscillator, okay, delta E is h bar omega. Right? This is spacing between energy levels. Okay? And so really, my assumption that T is much, much greater than theta V is equivalent to saying the thermal energy, kBT, is much, much greater than delta E. And this, as we said before, is the classical limit. Right? Okay. So all I'm saying is that this inequality is equivalent to taking the classical limit as I've just defined before. Okay, so we're going to take this limit. Look back at this equation. Does anyone tell me what we're going to do when we take this limit? If t is much, much greater than theta v, what happens to this exponent? The thing in the exponent is big or small?
Very, very small.
Very, very small. If you have an exponential of something small, what do you always do?
Where'd you get
Taylor expand. You can't say equal to 0, you can say equal to 1. That would give you the 0th order Taylor expansion. That wouldn't be super helpful. Usually you want the first order Taylor expansion. So you always Taylor expand, and then you always figure out what order the Taylor expansion gives you the first non-trivial result. And that's what you take. Okay, so you always Taylor expand. So we're going to Taylor expand an exponential. This is pretty much always what you do in physical chemistry. When you take a limit, you do a Taylor expansion, right? So we have in the limit that essentially KT is much, much bigger than h bar omega. We're going to write EV is n h bar omega. This thing, okay? We're going to write 1 over, and now I'm going to Taylor expand. So I'm going to take my e to the theta over t. I'm going to plug in what theta is now. Theta is h bar omega over k. So I'm going to Taylor expand. So the Taylor expansion of exponential, you should remember, right? It's just 1 plus x squared over 2 plus x cubed over 3 factorial, right? And we're just going to use the 1 plus x part of it, right? Where x is h bar omega over kBt. So it's 1, right? Plus my x is h bar omega over kBt. We're going to drop the x squared, the x cubed, blah, 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 because it's really small, plus dot, dot, dot. This is my Taylor expansion. Okay, and I still have the minus 1. Okay, and then I have to subtract 1, which is this minus 1, and then I have my 1/2 plus 1/2. Okay, everyone agree with that? So now, so this one cancels this one, okay? And I get EB equals n h bar omega, and this becomes flipped, right? So I get kBt over h bar omega plus 1/2. Okay, everybody agree with that? So now what I'm going to do, well, I said that h bar omega over kBt was really, 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 really small. So that means kBt over h bar omega is really, 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 really big, right? That means I can forget about the 1/2 if this is really big, right? So this is really big. Right, that's consistent with my ansatz here, and so I can drop the 1/2. So if I do that, then you see how we're going to get equal partition. I do that, I get EV equals, and my h bar omega here cancels this, and I have KT. Okay, so this is in the crazy classical limit where my temperature is way, way above 5,000 Kelvin. But we see we have equal partition. Why? We need 1/2 kBt average energy per degree of freedom. For vibrations, we have 2n degrees of freedom. That's weird, okay? Degree of freedom is sort of a misnomer. That's a sloppy way of saying it. The rigorous way of saying equal partition is you have 1/2 kBt average energy for each quadratic term in your Hamiltonian. Okay? Degree of freedom really means each quadratic term in a Hamiltonian. So degree of freedom is a little sloppy to say, but that's what you hear most of the time. For a free particle, you get away with saying degree of freedom because you don't have any potential energy, right? Here I had only kinetic energy. So I had 3 degrees of Vx, Vy, Vz. I had 3 quadratic terms in my Hamiltonian. Vx squared, Vy squared, Vz squared. Here I have 2 quadratic terms. I have x squared plus kx squared from the potential energy, right? So I have, for each particle, I have two quadratic terms in Hamiltonian, right? These two terms are a kinetic term. My kinetic energy is 1/2 mv squared, right? And so here's 1, my v squared, and then my potential energy is 1/2 kx squared. Okay? So you get 2 terms. So I should have 2 times 1/2 kBt, and so I get kBt worth of energy in each vibration. And n particles, that gives me my n. And so this is equipartition. Okay, in this crazy classical limit. Crazy because it's really high temperature. Everyone see that? Really important. Equipartition is so important because it allows you to estimate things for very complex systems like protein folding, right? So if you believe this, then you can start to estimate non-trivial processes, whether they're likely to happen or not happen. Okay, questions on that before we, well, 2 quadratic terms, right? So I get 2 times 1/2 kBt equals kBt for each vibration. Okay. Questions on that before we do rotation?
Wait, so we just showed that equipartition applies for a diatomic gas at super high temperatures.
Right.
But we're also saying that we can use it for like understanding protein folding or different like, complex
That's
systems
right.
as well.
that's an extrapolation, right? It's true. My proof in this class, well, maybe it'll be a homework problem. Maybe I'll find with them. I don't know. You can prove in general that equipartition holds whenever you have a quadratic term in the Hamiltonian. There exists a general proof of that. Here I'm just showing you, we'll see 4 examples. We'll see translation, vibration, rotation, and phonons. And so here, my proof is that it happens over and over again for every example we do. We can prove it rigorously if we wanted to, if we have time. For protein folding, what we'll see when we have phonons is, I say this is true for every degree of freedom. A degree of freedom could be complicated. It doesn't have to be a Cartesian coordinate. So for gases, a degree of freedom is pretty obvious. It's the coordinates of a gas. For phonons, the coordinates you care about are collective particle motions. And so you'll see that each phonon has 1/2 kBt worth of energy. But a phonon is not just a position. It's a collective oscillation between all the atoms in the crystal. So from that you can I shouldn't say easily. From that you can extrapolate to say, well, a vibration in a protein is not that much different than a phonon. A phonon is a collective vibration in a crystal. A protein folding is a collective motion among all the atoms in a protein that leads to some cooperative folding transition. And you can say that folding coordinate is much the same as a phonon. Because a phonon has 1/2 kBt, that folding coordinate should have 1/2 kBt, and then you can estimate, based on a folding barrier, whether it's likely to happen. So you can start coming up with these extrapolations that give you powerful insight. So that's a great question. Let's discuss that more when we discuss phonons. So bring that question up when we discuss phonons, okay? But it's really important when you start to think about degrees of freedom as not just being a simple Cartesian coordinate. You can apply it to any degree of freedom, even if it's a complex coordinate. as long as it's harmonic in the Hamiltonian. So that's a great question. Let's finish rotation and we'll be done. Okay? My marker is running out. Let's try this one. Okay. Rotation. Okay, rotation. Rotation's easy. Why is rotation easy? Because we already took the classical limit. Alright, so vibration, we didn't take the classical limit when we wrote down the partition function, that was exact. We had to take the classical limit here, but rotation we already took the classical limit, right? So ER equals KT squared. I'm using my formula which I erased, but you can look in your notes. It's KT squared d log QR dt. Okay, that's the formula we had before. Again, this is little q to the n, so the n comes in front, equals n kt squared d log little qr dt. Okay, and we already saw that in classical limit, q little qr equals, anyone remember? It's T over theta r. Okay, where theta r is the rotational temperature. Okay, it depends on the moment of inertia. Remember, this is in the classical limit already, because we had to convert a sum to an integral. Remember, we converted a sum to an integral to get that, so that means we're in the classical limit. So equal partition should fall out, because we're already in the classical limit. And I think you see that. This gives me ER is NKT squared d log T over theta R dt. Okay? And so basically I just flip this, right? ER equals NKT squared, right? And it's just going to be 1 over T, because I get essentially 1 over theta R T over theta R, right? Take the derivative of the log, I get 1 over this thing, and the derivative of this thing is 1 over theta R. And so this, my theta r's cancel, and ER is just N K B T. Okay, equal partition again. Why is that equal partition? How many degrees of freedom do I have for rotation? Is there any potential energy? Rigid rotor, no potential energy, right? Purely kinetic energy. If this wasn't a diatomic, I'd have 3 rotations, right? But because it's a diatomic, I only have 2, right? I can't rotate this way, right? So I can only rotate end over end. So I only have 2 degrees of freedom rotation for a diatomic, right? 2 rotational these are kinetic. For diatomic. Okay? And so of course we get 2 degrees of freedom times 1/2 kBT for each degree of freedom, and that gives me kBT, right? And so I have kBT energy for each diatomic. Okay, so that's pretty much it. That's all I want to talk about for the gases. And the really important point is equal partition theorem. Okay, so I'm out of time. So we're pretty much done with gases. So Macquarie chapter 6 is the last you'll see on these gases. We didn't discuss the homonuclear case. That's in Macquarie if you're interested. We didn't discuss polyatomic molecules. Macquarie discusses how you would do that. We're going to move on to crystals because we're running out of the semester. So we're going to move on to crystals so we can do crystals in the Ising model. So that's what we'll start next time, is we'll start crystals. Okay, great. So homework's due Thursday. I will post your grades today, and I will also send you guys a copy of your graded exam. And let me know if you have questions.